Welcome back, everyone. Today, we're demystifying something that feels almost like magic, but is actually 100% logical. We are talking about how computers physically store information. Yep, we're stripping away all the software to look at the exact raw electrical mechanics of memory. Okay, let's dive right into this. To really get how memory works, we first have to wrap our heads around a massive problem that early computer engineers faced. You see, basic logic circuits, which are called combinational circuits, are incredibly fast, but they have a fatal flaw. They're essentially just calculators with total amnesia. Sure, they process the current inputs you feed them to spit out a result, but the very second those inputs disappear, boom, the output is gone. They can compute, absolutely, but they literally cannot store history. They can't answer, hey, what just happened? Or what step are we on right now?
So here's our blueprint for today's explainer, so you know exactly where we're heading. First, explaining the memory problem. 2, meet the SR latch. 3, set, reset, and remember. 4, the forbidden invalid state. And finally, 5, metastability and system glitches.
Let's start with section 1, explaining the memory problem.
In the world of digital logic, there's a massive divide. On one side, we have combinational circuits. Their output depends entirely, and I mean only, on whatever the current input is. There's no memory, no awareness of time. And hey, they're great for simple tasks, like just adding two numbers together. But without memory, complex digital behavior, things like building a CPU, RAM, or even a simple counter, is just totally impossible. That's exactly where sequential circuits come into play. These are circuits where the output depends on the current input plus the previous state. They actually have memory. They're genuinely aware of time.
Moving right along to section 2, meet the SR Latch.
Early researchers made a truly fascinating discovery. It turns out if you take an even number of inverters, those logic gates that just flip a 1 to a 0 or a 0 to a 1, and you wire them in a continuous feedback loop, it creates a literal trap for the electrical signal. The output just feeds right back into the input, sustaining itself indefinitely. As long as there's power, that loop is going to endlessly hold a 1 or a 0. It's physical memory. But, well, a closed loop isn't super useful all on its own because we kind of need a way to tell it what to store and when to change, right?
Enter our hero, the SR Latch. This specific one is built using 2 NOR gates. As a quick refresher, a NOR gate is super strict. It only outputs a 1 if both of its inputs are exactly 0. Notice the elegant crisscross pattern in the wiring? The output of the top gate feeds directly into the input of the bottom gate and vice versa. So it maintains that continuous feedback loop we just talked about, but crucially it adds 2 external controls. We get an S input for set and an R input for reset. Plus, it gives us 2 outputs, Q and its exact opposite, QNen.
All right, section 3, set, reset, and remember. Let's see this in action.
Now, what's really interesting here is how we command the latch to save a piece of data. Say we want to store a 1. We assert our set state. We change that S input to a 1, and we keep the R input at a 0. Think of the S input as the builder. Its entire job in life is to force our primary output Q to equal 1.
Let's slow down for a second and trace exactly how that electrical signal physically propagates through these gates. Step 1. Because S is 1, the bottom NOR gate has at least one true input. That instantly forces its output, which is Qn, to 0. Step 2. That 0 travels right up the wire to the top NOR gate. Step 3. Now the top gate has 2 0 inputs coming in, one from R and one from Qn. So its output, our main Q line, flips to a 1. And boom, the data is officially stored.
But here is where the magic really happens. What happens when we take away the command? We drop both S and R back down to 0. The output Q remains a 1. The circuit has now entered the remember state. Even though our set command is totally gone, that crisscross wiring keeps the 1 and 0 flowing in a perfectly stable loop. It acts as this incredibly loyal memory keeper. Honestly, this is exactly what happens when you press the power button on your phone to turn the screen on and then you let go. You release the button, dropping that physical input to 0, but your screen stays on because the internal latch remembers your command.
Of course, eventually we're going to need to clear that memory. To do that, we introduce the reset state. This time we flip the script. We push the R input up to 1 and keep S at 0. If S is the builder, R is definitely the eraser. That 1 on the top gate forces Q to become 0. That 0 flows down, forcing the bottom gate to output a 1 on Qn. The memory is officially wiped clean.
And just like before, if we drop both of our inputs back down to 0, the circuit holds completely steady. It remembers the reset. It stays right at 0. Because this simple, elegant little circuit will happily just rest in either the set state or the reset state indefinitely, engineers refer to it as being bistable.
Which brings us to Section 4, the forbidden invalid state.
So, we have a working memory cell. It's brilliant. But, there's a catch. A strictly critical rule of the little universe we just built is that Q and Q naught must always be exact complements of each other. If one is 1, the other is absolutely 0. But what happens if we break the rules? What happens if we instruct the circuit to set and reset at the exact same time?
And this brilliantly illustrates the fatal flaw of our hero circuit. If you physically force both S and R to 1 simultaneously, well, because both NOR gates are receiving a 1, they are mathematically forced to both output a 0. Suddenly, Q is 0 and Q non is 0. We have completely invalidated the strict output requirement. This is known as the forbidden state. The circuit is electrically functioning, sure, but logically, it's completely broken.
Let's look at Section 5, Metastability and System Glitches. The forbidden state itself is bad enough, but it's actually what happens when you try to leave the forbidden state that absolutely terrifies engineers. This brings us to a concept called metastability. First, let's establish a baseline using a standard timing diagram. When S goes high, Q goes high shortly after. Notice the tiny horizontal gap marked T on a typical timing diagram? That is the gate delay. It takes a tiny fraction of a nanosecond for the physical electricity to actually travel through the silicon gates. In normal, everyday operation, the outputs respond predictably and reliably to the inputs.
But watch what happens if we're stuck in that forbidden state, where both inputs are 1 and both outputs are 0. And then we drop both inputs to 0 at the exact same microsecond. Both gates suddenly see 2 zeros, so they both try to output a 1. But as soon as they output a 1, they immediately feed that 1 right back to the other gate, which forces them back to 0. The circuit literally falls into a panic. The outputs will simultaneously and wildly alternate between 0 and 1. This highly dangerous condition is what we call metastability.
Just look at the chaotic mess it makes. Where the inputs drop from 1 to 0 simultaneously, you get this crazy oscillating cloud. The circuit is bouncing wildly inside there. Now, it will eventually resolve itself and settle into a state at some unknown point in the future, but, and this is the scary part, it will be a totally random state. And as you might guess, in computing, randomness and unpredictability are the ultimate enemy.
So, the absolutely crucial point here is that engineers must avoid metastability at all costs. There are basically 2 physical triggers for this glitch. The first is what we literally just saw, both inputs dropping from 1 to 0 at the exact same time. The second trigger is if the duration of our set or reset signal is just too short, specifically if it's shorter than 2 times the gate delay or 2 times t.
Let's look at why that second trigger happens. The path the signal must travel to actually lock in the memory means it has to physically travel through the bottom gate and then through the top gate. That simply takes time. If you send a command pulse that's way too fast, the electrical signal enters the bottom gate but shuts off before the result can make it all the way back through the top gate. The circuit gets totally confused, it doesn't know if it was supposed to flip or not, and boom, we trigger the exact same unpredictable metastable glitch.
We've seen how beautiful and elegant the SR latch is, but we've also seen its immense vulnerability. The simple act of timing a signal incorrectly can send the hardware into a chaotic tailspin. Which leaves us with a totally fascinating question to ponder. If the foundational memory circuit of all computers has this inherent physics-based flaw, how on earth do engineers build the ultra-reliable laptops, servers, and smartphones we use every single day? How do they actually tame this electrical chaos? Well, we will explore exactly how modern computer science solves that giant puzzle in our next explainer. Thank you so much for exploring this with me today, and I'll catch you next time.